everyone. My name is James Ramos, and I will discuss the six methods of the numerical. So, first of the six methods is the interhalves or bisectional method of iteration. So, what is bisectional? Bisectional is the essence of the numerical methods, where it is the easier way on how to get the estimated roots. So it can be used by both polynomial functions and transcendental functions. So first of all, we will solve the polynomial functions using the bisectional method of iteration. So first, we have the example of function that equals in x or x cubed minus 4x squared plus x equals to 10. So we have initial value of x of 0 equals to 4 and x of 1 equals to 5. So, and we have or we will get or we will have together the estimated root that less than or equal to 0.0001. So, how to solve or how to get the iteration or estimated iteration equals to or less than in 0.1. So 0.0001. So first, we have initial value of x of 0 equals to 4 and initial value of x of 1 equals to 5. So how to get the x of 2? So x of 2 is equal to round. So we get the function or function the decimal or round off or the decimal places in how many are numbers. So we have in this form the numbers or the formula we will use it. So first we have the formula that x sub 0 minus x x of 0 plus x of 1. Then divide it in 2. So we get wait we get and how many decimal places we will get 5. So we get 4.5. So in getting the functions, we will rewrite the function itself, but the x will be the value of the initial values, like x of 0 equals to 4. So first, in function x of 0, so it was round, then the function, so x of or x raised to 3 minus 4 multiplied by x raised to 2 and plus x minus 10. So why minus 10? Because when transposing the equal, we will need to change the sign of any numbers. So the decimal place again, and that how you get the functions or initial functions. So we repeat it in function x of 1 and function x of 2. So we will get 20 and 4.625. So now we get x of 2 or function x of 2. So we will rewrite it in absolute form. So to get the estimated root. So in absolute form value. So why I type value? Because when we type in equal, for example, when I type it equal to this box, or this cell, it will type even the formula itself. But in case of value, the answer or the main value of the cell will be added. Then absolute because we will because we need to get the main or the absolute value of the function x of 2. Then equals to then again that's the estimated root. Then it's great. So in root check, we need to check if it's true. If the estimated root is less than or equal to 0, or 0.0001. Then so now we have x of 2 or the new root. Then so in analyzing, if x or function of x of 2 is in positive side, we will copy the x of 2 in x of 1. So example, if so we type r for the initial value, then if it's greater than 0, then the logical test. If it's true, then we will copy the x of 2. Then if it was false or not accurate by greater than 0, then we will get or we will write x, the initial value or the previous value of x sub 1. Then for again, let's do that in the x of 0. So if for the logical test of x is less than, so we need to less than 0 because all the x at 0 in bisectional method is negative functions. Then so the if value is true, then we will get or we will copy x of 2, and if not, we will copy the previous value. Then so that's how you get the new root of or new second iteration of the bisectional method. So next, let's copy the formula itself. Let's copy again this formula of the function x sub 0 to x sub function x sub 2. Then let's copy the order. Then this, and let's copy. So that's how you get the initial value or how to use the bisectional method or iteration using the polynomial functions. So next, so in the root check, if the value of or the estimated root is is incorrect, then it means check or we get the initial or estimated root. Then let's move on to the percentage value. So like x of 2 or in polynomials, we need to get the functions here. Then so now you get the initial functions here, and that is how you get the transcendental function. like twice earlier. Just use the initial values and here and here. So getting another of the initial values. So wait. In these functions, I really forget that we have another types of functions. So let's again write the formula sine x or mean x of 0, then minus a to x and multiply it to exponential. Let's write the exponential ESP and then open close parentheses again. The initial and the power of the exponent x2, then x multiplied by x of 0. Then you will get um, you will get the initial value of 6.0 here, here. Okay. Now we get the in iteration. Let's write iteration here. Then 1, then 2, 1. So now we get the initial values in 0.01. In let's say in alterations 8 or 8 alterations, we get the estimated root of less than or equal to 0.0001. Let's move on to the regular policy. So regular policy is like bisectional method, but here in getting the x of 2, we have the formula that is equal to x of 0 minus function x of 0 multiplied by x sub 0 minus x of 1 over function x of 0 minus function x of 1. So here, let's use in the polynomial of polynomial. I forgot the regular policy or postposition can be used by both polynomials and transcendental functions. So first, we will solve the polynomial functions. So earlier, we had the same functions that equals to x cubed minus 4x squared plus x equals to 10. So getting the x of 2, we need to copy the function here. So like here, copy the function. So we have the initial functions of x of 2 or x of 0. Then we have x of 1. So we met the conditions in getting the x of 2, where we have the x of 0, we have the function x of 0, we have the function x of 1, and we have the function of, or we have the value of 1. Then in getting, so let's move and number, so the formula, so x of 0 minus here we need to open close parenthesis, this 2 for function of x, what? For x of 0. So let's write I 12. Then multiply by first the numerical or numeric numerator. So let's move to x of 0 minus x of 1. And then divide it by the functions of, let's divide it by functions of I 12 minus j 12. So drop out of random decimal places. Then here we get 4.0.23077, the x of 2. Then we have the functions of x of 2 equals to negative 1.63858. So like a bisectional or bisectional method, we have to rewrite if the function of x, if the function of x is equals to 0 or equals to negative sign of numbers, we have to rewrite the x of 2. But if not, then rewrite the previous value. The next we have the initial value here, like earlier from the exceptional, we need to copy the, if the sign is positive, then we need to get the x of 2. Then right again until you get the initial value of y or the estimated root. So like earlier, the so iteration to so in the eighth iteration again, we get the iteration of or the initial value. So next is transcendental. So transcendental, like earlier transcendental, let's copy the formula of the function itself to get initial value. So function get the initial values here, then exactly. So and we will get the initial value. So we have the root check and we get the initial value here. The first alteration we get the root check or the estimated root itself. So that's how you use the regular function. So let's move on to second method. So in second method, it is the same of the regular function, but in terms of using the initial roots, you need to copy the x of 0 or x of 1 and x of 2. So, so let's move on to the functions. So here we have functions equals to, again, let's move on to the functions. We again copy this. So the earlier we get the functions of x of 2, then copy it here. So we get the initial value. Then getting the new root equals to 1. Then getting the equals to value again for the main. So here we get the x of 2 again, and let's again write it here again. Then we get the initial value of here. Let's copy this. So we have the initial values here. So in the fifth alteration, we get in the fourth alteration, we get the value of the estimated root. So let's move on to the first method. So second method again can be used by polynomial function and precedental function. So let's move on to the function of precedential function. So let's give here the initial value of x of 0. So here, then functions, then again here. So here we get the estimated again. We get the estimated root in the first alteration. So let's move on to Newton's method. So Newton's method consists of getting the x of 1. So here we only need x of 1 or x of 0, the function of x of 0, and the derivative of x of 0. Then, so getting the x of 1, first we need to find the x of 0. So initial value again, the function of x of 0, x of 0. Then we get, here, because this is a derivative. So derivative, what is the derivative of the function x here? So we need to use equals to. So the derivative of x of 3 or x cubed is 3x raised to, right, count the function 3 and x 3 of 4 raised to 2, because that is the derivative of 3x or x cubed. So let's move on to 4x squared, then minus 8 multiplied by x. So the derivative of 4x cubed is 8x. Then let's move on. This is simply 1 because x or derivative of x is equals to what? So that's y. Y. So, so that's how you get the estimated or the derivative of x of 0. So let's move on to x of 1. So x of 1, x of 1. So we have the formula that equals to, so x of 0, x of 0 minus function of x of 1. So function x of 1 divided by function or derivative of x of 1 or x of 0 means x of 0, function of x of 0, then decimal places again. Now we get the x sub 1. So let's rewrite the value of x sub 1 here to get the value of x sub for new root. So but before that, we need to copy the initial value. We here copy the value here, then here. But unlike this, we need to use 14 as the number x, and then it looks like it's not, then this means this is nowhere to be undone. So now we get the initial value of -6. So we have the first again equals to absolute value or value absolute equals to f of x for initial or estimated root. So here we have again copy the formula here to get the formula. So that's how we get the initial value of the check means here initial again, initial, then initial function. And here we need to copy the x of 1 equals to value x of 1. We get the initial value. So by getting this here, the third calculation to get the estimated root that less than or equal to 0.000. So let's move on to the precedent time function. So the special particular function of x sine x equals -2x exponent of x squared x 2x. So we need to say again, we need to copy the okay, we need to copy the function again here, then move on to this about let's move it here to get functions of x. Then here, having to difficulty, the derivative of sine x is equal to cosine x, cosine x, right? So cosine, wait, you forgot the wrong cosine, cosine of x of 1. Then plus 1, but plus 1, right? Plus 1, plus 1. Then the minus Then derivative of x e raised to 2x, then we have 2 multiplied by x squared. Why x squared? Because so when derivative being exponential, we need to down the exponent itself. So here 2, then multiply it again to exponential to x, the power of x, and then I mean so initial one again 5, okay, plus 1. What is the problem here? So there's no problem, just some typo. Okay, looks like some, what is it? Ah, so let's equal to, so we have the functions here again, then copy the formula here, we get the precedential functions, then you see here, then copy this the function right here, so we get negative 10, here we get the final root or estimated root, so equals to the estimated root again, copy the formula, then until we get the estimated root. The deepest estimated root, so I will start here. The function, so until we get the function itself, because this is not quite literal across-dental functions, then it is always getting higher or lower, higher or lower. So let's move on and let's use 0 for estimated root. Then we get again 0.1 accidental use because this is a non-functional, so it's impossible to get these precedental functions by using the Newton's method. Let's go on to test it. So again, fixed point alteration. So fixed point alteration is unlike the other formula they using triangles. Fixed point alteration is used to get the y from the function itself. For example, or next, fixed point alteration can be used by both polynomials and precedental functions. So let's move on to polynomials. So polynomials, we have functions or example function of equals to x to cube minus 4x squared plus x minus 10. So we have that kind of function. Then equals to, let's move on to x equals to, so getting the particular formula, we need to use y equals to 4x squared minus x plus 10. So x minus 10 again and again here. So getting the function of x, we simply use the formula itself here. We're getting the x n plus 1. Hmm. Then this is how to get the function. So here, here we have the function x of 0 equals to -10. Then here we have the function of x of 1. Then using the x value, I mean here, let's move it here, then here, then we have the initial value. Getting the initial value again until x of n is equal to functions itself. Then here, we, like Newton's, you need to just copy the x n plus 1. Then it equals to value x n plus 1. Then S is again the initial till right. That's why I think right. Where we get the here, the value here, and here, the formula here, then here, we can we get the formula itself. Getting it here, and here, right. That's nothing. Let's evaluate the errors of confirmation steps. Ah, that's why we get x of 0. Oh, so that's why that didn't quite get it. Because this formula used to list f for x here, here. That's how you get function itself. Let's move on here. Then now we get the functions. Y, so like that here, just copy the formula. You get the transcendental function. So absolute till to satisfy the exponential, the estimated root. So we get the polynomial function. So next residential functions like earlier. So this will be used in sine x. So we need to say x of 1 is equal to equals to the sine sine or I mean arc sine x to x sub 1 multiplied by exponential 2 multiplied by here. Number. So that again. So calculation sine. So here transcendental functions cannot be solved because it's too high or mean. Let's change the initial value of x of 0. So that's we get the function itself. So function of x of 1 again. We interpret the functions here. So we have function 10, but so here the function of x of n. So then equals to again initial value copy you until satisfy the 0.001. So let's standard if we get the initial value. So here we get 5. Here now it satisfied it, right? So it said then here we need to copy the product we have. So here again checking value no. Here no. So let's set it again. Until it satisfies the initial estimated root. So let's move on to Miller's method. So Miller's method, this is the complicated method of. So Miller's method is only be used by polynomial functions. So let's write it down the function itself. So here it had x of 0 or initial values of x of 0, x of 1, and x of 2. So 3, 4, and 5. 5 is the initial values itself, and the function is equal to. Now let's copy the formula here, but let's change here, here. So the initial values itself, then getting the functions, and so getting the x of 3. So that is 2 for again to get the x, y until e. So here let's again copy this cell. So here we get the initial values. So initial value again. So the formula from getting the h is in 4 minus 2. So 4 minus 3, the subtraction of equals to the subtraction of 4 is then mean from the subtraction of 0 or x of 1 minus x of 0. So that's how we get the h of 1. I mean that the decimal places. There's a copy saying here, here, and here. So that's how you get the h of 1 and h of 2. So getting the xi x of 0, then we have the formula of x of 0 that equals to function of x of 1. So round equals to round y function of x of 1, right, x of 1, then minus a2 function of x of 0. So then all over H or H1, H0 or H4. Can be fetching anything from here. So the equals is the particular method, a particular formula we have given that. Let's copy the multiple again here. S of 1, unlike S sub 0, S of 1 has the same formula for, looks like it has the same formula again. I'm sorry about that. For S of 2 is equal to, meaning to say into 3. Looks like I forgot S of 2 is not E, not E. So let's move on to A. So A has the as formula that equals to, let's write S1, so S1 minus beta S1 minus 0 or S sub 2, S sub 0, S sub 0, then divide or over H plus 1, or H1 and H2. So H1 plus H2. So then we have 8 equals to 8. So next is B. So another formula, B is equal to round, and using B equals to 8 multiplied by H1. So I mean H1. Then plus S1 or S of 1. Then we have the value of B34. So next, C is only equals to S sub or function of x2. So let's copy the function x of 2 value equals to x of 2. Then here we get wait. Let's rewrite again the formula. So D, so D, in D, we have the formula equals to square, square, square root of so B equals to square root of B raised to 2 raised to 2 minus 4 multiplied by 8, then multiplied by C. So we get 23. So 23 or that, so 22.7163 the D. Then substituting again the formula here. Then now we met the condition in getting the x of 3. So we have the formula again. Round and x. Round here. In getting the x of 3, if the b is in negative form, the b will be in negative form then. Then if b is in positive form, then shall the b is in positive form. So let's move on. So typing in for the condition and logical if b is zero, less than zero, then the condition we need to met is x x x sub 2 will be added to the negative 2 multiplied by c. So we have c all over all over all over b plus b plus b. So, so in another formula, if the b is in negative form, then we will type it in h9. Again, h9 h plus again formula. So again here -2 multiplied by c9. So so is c yes c then all over b minus b. So that is the condition in getting the answer. So we have get the value of 1.455277. Okay, let's look on here. Looks like I did it. Let's get it on here. Okay, let's get 26. So it's what so formulate 7 until we get or satisfy the initial value. So copying to get the functions, copy the x of in x of 0, copy just the value of y. So value x of 1 here, then, until we get the functions set. So here we get the initial function e, then er equals to, but wait a minute, something I tried here. So y is this plus so -2 multiplied by plus plus here, right? So we specify the function itself, then how to get the estimated root, then we have the formula of estimated root absolute value equals to round, then absolute value of x x of 3 minus yeah, x of 2 minus x of 2 x of 2 all over x of 3. Then getting the initial value again, then multiply it by 100. So 5 of x. So we have 16, then copy the formula is satisfied. Until the terminating is until the termination or get the terminating. So click again. So then here get functions here, copy. Then till the estimated root is 0 point less than. That's how we get or how to use the Miller's method. So that's all, and thank you for listening and watching.